And so the question is, what can we do with all these plastics that we as humans have created? And when we think about what plastics are as a whole, we know that plastics are hydrocarbons. And so if there was some way that we could somehow change the structure of these hydrocarbons into a different molecule that was more useful to us, then we'd have a great process in place. And so when you burn plastics, you are actually generating more energy than you put into starting the fire in the first place. And so in a lot of places, the way they get rid of their plastic trash is they literally burn it, and they use the energy from burning it to heat up their process, like having a steam turbine to power some homes in your community. The issue with that, though, is that these plastics are releasing a bunch of very toxic materials when you burn them, so burning them outright is really not that great of an idea. What you can do, however, is that you can make use of heated steam and oxygen to do kind of a more slow cooker process, in which, because you're controlling the rate of your reaction much more effectively, we're able to get out a syngas from this process. And so what happens, and what a company called Sierra Energy is doing, is that they use this thing called a blast furnace, which is basically just this big bowl, and it's just like this, except a lot smaller, or bigger in this case. But basically what they do is, inside of this blast furnace, the top of the blast furnace will be where you can place your solid waste materials, like the plastic bags you get at a grocery store, and then another plastic bag that supposedly people would reuse, but I think most people don't. That goes into the top of your blast furnace, and then at the base of your blast furnace, what you have is a stream of superheated steam and an oxygen. So these are going into this process. And so what happens is that the superheated steam is providing energy, and the oxygen is also going to be reacting with the hydrocarbons inside of these solid wastes that you're putting into your blast furnace. And so what comes out of this process is an effluent stream that is syngas. And syngas is very useful to us because we can use syngas to do things like make ammonia very quickly. And ammonia is used in our fertilizers. We can use syngas to create jet fuels or diesels that we can burn. And we can also use syngas to make stuff like hydrogen gas that can power stuff like hydrogen cars or other types of commercial processes. So that is the cool thing that we can do with these blast furnaces, and by doing a process referred to as gasification, is that we're able to take these wastes and actually turn them into useful products that we can continue to use. The one issue is that as we run our process and we generate syngas, these plastic wastes, about 90% of them are able to be turned by weight into the syngas that's actually useful to us. However, 10% ends up being just like this black lump of stony material. And so if we want it to be 100% weight efficient with the solid wastes that go into our blast furnace, we could use that in construction materials. So basically we'd be entirely reusing all of the waste that goes into our process. The other big issue, though, and this is probably one of the biggest issues that people face in terms of actually implementing these blast furnaces in the real world so that we can actually start making a dent in terms of our footprint, is that the variety of trash that can come into your process is so variable, because, you know, some rando can show up the next day and just have weird types of plastic and this other stuff. So figuring out how can you make a process that is adaptable enough to the types of trash that you're going to be putting into it to still create a syngas stream that is high enough quality for people that can use it downstream productively is a very big challenge. And so those are the big issues that we're currently facing in terms of implementing these processes and scaling them up. But one of the very interesting parts of this too, in terms of a solution, is that when we look at the energy balance of our overall process, we know that, you know, if we're producing 100 watts equivalent of syngas from our effluent stream, the process to power the generation of that 100 watts of syngas only took 20 watts of energy in terms of heating up that steam and putting in that oxygen into this actual blast furnace. So what that means is that as a whole, this process is actually producing 80 watts positive net return on running it. So by taking in these plastics, which, you know, we didn't pay anything for in terms of energy, and by heating up that steam with 20 watts, we're able to generate 100 watts of syngas. So these processes can be entirely energy independent and also do more than just be independent, but provide energy for other purposes like if we wanted to, we could burn this and use it to power a steam turbine so that we could heat up or provide electricity to local cities. So these processes have the potential to be very cost-effective solutions to problems that we have, which is what do you do with all this trash, and not just how do you sequester it, but how can you do something that's productive with it so it's actually a commercially viable operation to do in the long run. So that is the key takeaways from this, is that we can be doing some very interesting stuff right now with gasification processes in terms of how do we reduce our footprint, how do we get rid of wastes, how do we change our waste into stuff that isn't waste anymore but something that's actually valuable to us. And so I'm going to end things with that. Thank you all for watching. Let me know if you have any questions, and take care.